Okay, so it appears that I made an error in the calculation of Young's modulus for this problem question 12. So I will solve it again once more here. Okay, so the question asks, determine the maximum uniform strain ductility of the brass whose stress strain diagram is given below. And in the part B, initial gauge diameter is given as 10 millimeters. Calculate the final gauge diameter at 200 megapascals of stress, and Poisson's ratio given as 0.33. So first, if you look at this inset here, so yield strength is given as 250 megapascals, and this is the 0.2% offset line, but this point here corresponds to a strain at yielding of 0.0046. So if we rewrite the problem statement, so ductility is asked here, which is the final length minus initial length divided by initial length times 100 in terms of percent elongation. Okay, now when we fracture the specimen, it will unload in such a manner. The unloading will be parallel to the elastic portion of the curve, and the strain at fracture will be different from the final length value that we measure. So in order to find this final length, we need to find the amount of elastic unloading here. So in order to do that, we first calculate the Young's modulus, E, which is the, we use the inset zoomed in portion of the curve. So the stress value that we know is 250 megapascals. And Young's modulus or elastic modulus is basically the slope in the linear portion. So if we take a look here, we can say that the slope here is going to be sigma yield minus 0 divided by strain at yielding minus 0.002. So if we rewrite this, then Young's modulus is going to be 250 megapascals divided by 0.0046 minus 0.002, and that turns out to be 96,153.85 megapascals. You can round this to, in terms of gigapascals, 96.2 gigapascals. So that's the Young's modulus for the problem, for the material. Now, from the same stress strain curve, we see that the fracture strength, let's say the fracture strength is going to be 400 megapascals. Then the elastic unloading strain, this part here, is going to be basically the fracture strength divided by the Young's modulus. So fracture strength is 400 megapascals, and the elastic modulus is 96,153.85 megapascals. Then the elastic unloading is going to be 0.00416. So the fracture strain at this point is going to be, let's write it here, fracture strain is going to be 0.37, and the elastic unloading is 0.00416. Then the difference between these values gives the plastic deformation, and the plastic deformation is directly related with percent elongation of the specimen. And if we calculate the plastic strain, it's going to be 0.37 minus 0.00416. That turns out to be 0.36584. And if you multiply this by 100, you get that percent elongation is approximately 36.6%. So not much has changed. The amount of deformation is still around 36%. But the results of part B changes significantly for this problem. In part B, the initial gauge diameter is given, the final is asked to us, and the Poisson's ratio is given as 0.33. The stress applied is 200 megapascals. So from the previous part, we calculated the Young's modulus. And if we examine the stress strain curve, we see that the stress value is less than the yield strength. We are somewhere here. So since the stress is less than the yield strength, we say that the Hooke's law is applicable. Then let's apply the Hooke's law. 200 megapascals, and the elastic modulus 96,153.85 megapascals, and we need to calculate the strain. If you divide these values, we get the strain as 0.00208. Now for uniaxial tension, if we load the sample like this, and these are our coordinate axes, the Poisson's ratio is defined as strain in x direction divided by strain in y direction. So we calculated the strain in y direction, and the Poisson's ratio is given to us 0.33. If you multiply these values, the strain in the diameter is going to be minus 6.864 times 10 to the power minus 4. The minus sign is there since the elongation in length causes a reduction in diameter. Okay, so the strain in x direction is going to be defined as change in diameter divided by initial diameter, and so the change in diameter is going to be epsilon x times d0, so minus 6.864 times 10 to the power minus 4 times 10 millimeters. That's going to give you minus 6.864 times 10 to the power minus 3 millimeters. Again, there's a reduction in diameter. Final diameter is going to be initial diameter plus change in the diameter. So 10 minus 864 10 to the power minus 3. That's going to give you 9.99 3136 millimeters.